Questions 21 through 25 of the 1998 Grade 7 Gauss Math Contest is what I will cover in this video. 10 points are equally spaced around a circle. How many different chords can be formed by joining any two of these points? A chord is a straight line joining 2 points on the circumference of a circle. Okay, let's draw a circle. And let's draw 10 points that are equally spaced. So we'll draw them in let's say red. So here's our first one, second one, we'll get 10 points, right? So here's one, here's another one. In a very approximate way, I'm trying to make them equally spaced. And I think I did a pretty good job. So you got 10 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they're going to draw some chords like this. That's basically a chord. And they want you to figure out how many is the total that you can create. Well, the first series of chords that I just drew, how many were there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So from this point, I've created 9 chords. All right. Now let's see if there's a pattern or something happens that will kind of give us a clue as to how to figure this out. Let's go now to the next point, which is right here. And let's use a different color. And let's start drawing the chords. Now, the key word here is different. It's got to be different, so I can't overlap what I've already done. So here's 1, 2, 3, 4, 5, 6, 7, 8, and that's it. Because if I go from here to here, that's an overlap, so I can't do that. So basically, I've done 8 new chords. All right, let's keep going. You probably already have an idea of what's going on here, but I'm going to keep going just in case. I'm going to go over here and I'm going to draw some chords. Again, can't overlap. 1, 2, 3, 4, 5, 6, 7, and that is it. Because if I go here, I'm going to do an overlap, and if I go here, I will do an overlap. So I've got 7 from here. And similarly, if you go around this circle, you'll find that you'll get 6 new chords here, 5 new chords here, 4 new chords here, 3, 2, and 1, and by this point you will have exhausted all the chords. So the total number of chords, you just add up these numbers. So you've got 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Now, I want to mention something. There's a formula that you can use to add up consecutive numbers, and it's n times n plus 1 over 2. And in our case, it's not that many numbers, right? You can easily do this in your head or on a calculator. But if you have a very long, like 1 through 4,000, you're not going to sit there with your calculator going 1 plus 2 plus 3 plus 4. So this is a very nice formula, and this is going to come up again and again. It'll probably even come up during this video again. So n is, of course, representing the final number. So if we put that in, you'll get this 9 times 10 over 2, which is, of course, 45. And that would be choice B. Each time a bar of soap is used, its volume decreases by 10%. What is the minimum number of times a new bar would have to be used so that less than half of its volume remains? All right. instead of using X and that kind of stuff, I'm just going to give the soap a weight. I'm going to say it's 100 grams. It'll just make it so much more easier than to use X and X over 2 or 0.9X and all that. So I'm going to make a little graph, or a table rather, of how many uses and then how many grams are remaining. And this should be pretty clear. So when you first start off, it's 100. After one use, you will lose 10%. So basically what you're doing is you're multiplying by 0.9 each time. And I'll do it on the side right here. So the first one, 0.9 times 100, is easy. That's just 90. So this is how many grams are remaining after one use. And then after 2 uses, you take another 10% off of this. But you don't do that by subtracting 10. That's the wrong mathematics. You have to do 0.9 times 90. Okay, 0.9 times this number, and that's 81. So these 81 grams of the soap bar are remaining after 2 uses. And you just keep going. After 3, it would be 0.9 times 81, which is 72.9. And then after 4 uses, same thing. And that would give you a value of 65.6 approximately. After 5 uses, again 0.9 times 65.6, and you are going to get 59.0. So we're getting close to half of the volume. I think we should get it within the next couple of uses. So 0.9 times 59 gives you 53, so we're almost there. We're still not halfway. We're close. And then the last one, I believe, should do it. 53.1. The 7th use, or after the 7th use, you get to 47.8. So it takes 7 uses of this bar to get below 50% of its original weight. So that would be choice C. A cube measures 10 by 10 by 10. 3 cuts are made parallel to the faces of the cube, as shown, creating 8 separate solids, which are then separated. What is the increase in the total surface area? So let's take this one step at a time. Let's draw a cube and see what happens. So here's our cube, and I've drawn it to make it look more like a 10 by 10 by 10 cube, which is what they say in the question. In this one, it kind of doesn't look like 10 by 10. This side looks much shorter than this side and that side, but that's okay because they're not drawn to scale. They're just drawn as a means to be an aid to you. So first, before we get into all the cuts and all that, this question is talking about surface area. So they want us to figure out the surface area first of this cube, and then the total surface area of these 8 pieces, 8 separate solids. So first, let's just do this one here. It's 10 by 10 by 10. So surface area is basically the area of all the faces. And a cube has 6 faces. So we've got 6 faces. Surface area, SA, and each face has an area of 10 by 10. It's basically a square. So 6 times 10 by 10, which is 100, and therefore the surface area of this cube is 600. It's pretty straightforward. Now let's turn our attention to this one. What did they do in this question? Well, they cut it like that. They've cut it all the way down, and they've cut it across like that. And when you do that, you make 8 different solids. And they've shown that in this diagram. And it's a helpful diagram. 8 separate pieces. Now each of these separate pieces I will draw out. So here is one of the separate pieces, one of the 8 separate solids that they are talking about in the question. And what are its dimensions? Well, this full side was 10. So if it was cut like the way they show, then you are going to make 8 separate solids. So therefore this is going to be 5, the length. And similarly, if this was 10, this is going to be 5. So that's 5 and 5. Okay? And then similarly, this part of the cube will also be 5. The question really doesn't give us a lot of information. We're kind of going a lot by intuitive assumptions here. Also, with this graph, we're just assuming that the cuts are made in the middle. And I really kind of thought about this, and considering it's a grade 7 exam, I really don't think they're going any deeper than that. So now let's just figure out the surface area of this one shape. Well, again, it's 6 sides, and all 6 sides have the same dimensions, 5 times 5. So it's going to be 6 faces, and each face has the dimensions 5 times 5. So this is 6 times 25, which is 150. Now remember, there's 8 of them. So the total for the 8 solid pieces in terms of its surface area would be 8 times that. And that is, of course, equal to 1200. So what is the question asking us? What is the increase in total surface area as you go from this to that? Well, you had initially a surface area of 600, and then you went to a surface area of 1200. So that is a increase of 600 when you go from 600 to 1200. So that would be choice D. On a large piece of paper, Dana creates a rectangular spiral by drawing line segments of lengths in centimeters of 1, 1, 2, 2, 3, 3, 4, 4 as shown. Dana's pen runs out of ink after the total of all the lengths he has drawn is 3,000 centimeters. What is the length of the longest line segment that Dana draws? All right. So she, or he rather, sorry, Dana is a he, is drawing 1, 1 like that, then 2, 2, then 3, 3, 4, 4, and I'm assuming that this just goes on like that. So we got 1, 1, 2, 2, 3, 3, 4, 4, and like I said, our assumption that it's 5, 5, 6, 6, but you can also see that from this diagram. If you go in that rectangular spiral type of path, it will increase by 1 each time. So it will be 6, 6, 7, 7, 8, 8, and then so on. Now, when Dana gets to a total length of 3,000 centimeters, pen runs out of ink. So we want to know what is the longest line segment that Dana draws before running out of ink. So we have to add these lengths. So it'd be 1 plus 1 plus 2 plus 2 plus 3 plus 3 plus 4 plus 4, and so on, all the way up to something, we don't know, all the way up to some number, n. And that is going to equal 3,000, or it will come near 3,000. So how do we do this? Well, if you remember, right in this video earlier, I told you that there's a formula for figuring out the sum of consecutive digits like that. If you have a bunch of consecutive digits all the way up to, say, n, that is equal to n times n plus 1 over 2. All right, very helpful in this question. So in this scenario, we've got 1 plus 1, 2 plus 2, 3 plus 3, like that. So what I'm going to do is I'm going to say there's two n's as well, just to make my life easy. And therefore this becomes 1 plus 2 plus 3 plus 4 all the way up to n. And then there's another round of that, 1 plus 2 plus 3 plus 4 all the way up to n. So do you see what I did there? Equals 3,000, or comes close to 3,000, we don't know. I just split up the question into two parts. And the reason I did that is so I can use this formula. So this first one becomes n times n plus 1 over 2, and then this next one is the same, n plus times n plus 1 over 2. And again, it's going to be equal or close to 3,000. Well, this basically just becomes n times n plus 1, because you have half and half, and that equals 1. Now, what do we do at this point? Well, what I did was, you have n times n plus 1 is equal to 3,000, right? So it's very close to being n times n equal to 3,000. It's very similar. So to kind of approach or figure out what n could be, instead of doing this as a polynomial and quadratic formula, which would take forever, I just took the square root of 3,000 just to get an approximation. And if you take the square root of 3,000, you get a value of about 54. 54.77 to be exact. So my hunch is that n, since n is a number, it's not a decimal, n is probably 54. But I don't know that 100%. But let's go with 54. So if n is 54, what do we have here? We have 54 times 54 plus 1, and that is going to be equal to 2970. So that's good, right? That means that when Dana gets to 2,970, he has essentially drawn 1, 1, 2, 2, 3, 3, all the way up to 54, 54. And then he's got 30 centimeters remaining to get to that magical 3,000 number. And up until this point, it was 2,970. So what is the question asking us? The question is asking, what is the length of the longest line segment that Dana draws? Well, he drew line segments of 54 in length before he drew one final line segment of 30 in length before he reached 3,000. So the longest line segment that Dana drew is 54. So that would be choice C. Two natural numbers, p and q, do not end in 0. The product of any pair, p and q, is a power of 10. That is 10 or 100 or 1,000 or 10,000 and so on. If p is greater than q, the last digit of p minus q cannot be. Okay, so let's try to understand the question before we tackle the question. P and Q do not end in 0. All right, so that means P cannot be 10, P cannot be 20, that kind of thing. The product of any pair, so if you multiply P and Q, it's going to be a power of 10. So 10 to some power. We don't know what power. And then they're telling us that P is greater than Q, and they want us to figure out P minus Q, and then say what is the last digit of this number. So the first thing I noticed is not much information given, but we can work with this. 10 to the power of n is broken up into 5 and 2, like that. And since P is greater than Q, P I will let equal to 5, and Q I will let equal to 2, like that. So this becomes 5 to the n times 2 to the n. And then what we have to do is we have to make a table and see what we get. So we're going to make a table for P, for Q, and then P minus Q, which is what we've been asked to find, for values of n. And the hope with these style of questions is that you're going to get some sort of pattern, and that pattern will help you greatly. And sometimes the pattern comes pretty quickly, and sometimes the pattern takes absolutely forever to get to. It depends on the question, but I'm anticipating that since this is a grade 7 contest, the pattern will come relatively quickly. All right, so when n is 1, we have P is 5 to the power of 1 right here, which is just 5, and Q will be 2 to the power of 1, which is just 2. You see how I got that? When n is 1, P is 5 to the power of 1, and Q is 2 to the power of 1. So those are the values for P and Q. So P minus Q is 3. And therefore, what is the last digit, which is what they're asking for? The last digit? Well, it's just 3. All right. Now let's try n equal to 2. When n is 2, P is 5 to the power of 2, which is 25, and Q would be 2 to the power of 2, which is 4. P minus Q is therefore 21, and the last digit of this number is 1. All right, so far so good. Let's keep going here. When n is 3, P is 5 to the power of 3, which is 125, and Q is going to be 2 to the power of 3, which is 8. And therefore P minus Q is 125 minus 8, which is 117. 7 is the last digit. 4. When n is 4, P is 5 to the power of 4, which is 625, and Q is going to be 2 to the power of 4, which is 16. And 625 minus 16 is 609, and therefore the last digit is 9. Now I want to stop here and go back to the question. The last digit of P minus Q cannot be, well, cannot be, I think we've done it so far. We have a 3, so it can be 3. We have a 1 here, so it can be a 1. We have a 7 here, so it can be a 7. And we have a 9 here, so it can be a 9. The only one it cannot be is 5. The only choice that it cannot be is 5. So the answer is C.